Hello, everyone, and welcome to our second webinar this month, Memgraph at Scale, Analyzing Company Ownership and Supply Chain Networks with a 2 billion node graph. My name is Maya Natarajan, and I'm VP of Product Marketing at Memgraph. I'm very pleased to be joined by James Conkling, Senior VP of Product Engineering at Sayari. Before we get started, let me share some housekeeping rules. Today's webinar is being recorded. We will share a link with you after the event is complete. We also invite your comments and questions. Please note that there's a Q&A box on the right-hand side of your screen. If you have a question at any point in time, just type it in there and we'll get to those at the end of the event. Alrighty, let's begin. What I'm going to do right now is start off with a quick 5-minute introduction to the Memgraph hybrid architecture and how it lends itself to different workloads. For those of you unfamiliar with Memgraph, it's a property graph database that has been built natively for in-memory data storage and analysis. It has 3 modes of operations based on workloads. First is the in-memory transactional mode that's used for applications requiring immediate responsiveness. This storage mode offers all asset guarantees. Write-ahead logging, or what are called wall files, and periodic snapshots are created automatically, and snapshots can also be created manually. The benefit of this mode is that it provides high performance with minimal latency. However, this mode is limited to available RAM, so it's not conducive for extremely large data sets. The second mode is the in-memory analytical mode, which is used for concurrent execution of complex analytical queries. The benefit of this mode is speed. This mode, like the in-memory transaction mode, is also limited by available RAM, and it has no asset guarantees. Because of no asset guarantees, data loss could occur if the system crashes. To prevent that, Memgraph allows for manual snapshotting to recover data as much as possible. Now, the in-memory analytical storage mode that I just talked about doubles as a separate graph analytics engine. Here's how it's done. I'm going to walk you through it. The first thing we need to do is to turn on Memgraph in the analytical mode. Next, we can ingest data into Memgraph very quickly and in parallel. As I mentioned earlier, there are no asset guarantees in this mode, which is actually what allows for really fast data ingestion. You can migrate data from different sources or files, or it can do a pure ingestion via clients. Next comes the analytics. This mode is set up for OLAP querying using Cypher. To enhance performance further, what Memgraph has done is that we've built in graph algorithms to the core, specifically what we call the deep path traversal algorithms, such as DFS, BFS, all shortest, and many others. Now, once we get the results of the analytical queries, we can export data out to any database. It can be S3, Snowflake, Postgres, and many, many others. Memgraph can then be shut down as it's no longer needed, providing RAM back to the machine for in-memory transactional processing, as that's the default mode. Now, used this way, Memgraph is a pure standalone graph analytics engine, since storage and compute are totally separate. Here, data is brought in, analytics are carried out in the in-memory analytics mode, and then data is exported out to a source of truth database, which could be any type of database, a relational database, NoSQL database, a graph database, if you wished it to be. Okay, not to forget, there's a third mode, so let's get back to that third mode in the hybrid architecture, and that is the on-disk transactional mode, which is used when there are large data sets that exceed RAM. This mode also has asset guarantees. Now, the biggest advantage of this mode is, of course, scalability. The trade-off here is lower performance with higher latency caused because of slower access to data due to disk I/O operations. Now, by utilizing this hybrid architecture, Memgraph delivers enhanced performance, speed, scalability, and most importantly, reduced total cost of ownership. So you see that Memgraph provides the entire package here required of any graph database. All right, what I'm going to do right now is finish off very quickly with when these different modes are used. First, the in-memory transactional mode. This is used when you need performance and low latency transaction processing. That is how PaySure, a payment authorization company, is using Memgraph in the in-memory transactional mode to process payment authorization requests. These requests involve receiving over 100 fields of data from payment networks. This data is processed within very tight deadlines and then used to decide whether a transaction should be approved or declined. By using Memgraph in this mode, PaySure has reduced authorization response times from 200 milliseconds to less than 10 milliseconds. So that's a 95% decrease in response time. Now, if you're interested in learning more about PaySure, check out our webinar from earlier this month. That was the in-memory transaction mode. Now let's take a look at when the in-memory analytical mode is used. It's used for rapid analytical queries and when you want to do really quick parallel data imports. I'm not going to give you an example here, as that is what James Conkling from Sayari is going to talk about. Basically, how Sayari is using Memgraph in the in-memory analytical mode, but with a twist. Okay, and so with that teaser, I'm going to hand it to James. Let me stop sharing here. And James, while you're getting ready, let me remind everyone that there's a poll that we'd like you to take. In this poll, we'd like to know where you are in your graph journey. Please respond to this as it'll help us tailor those webinars for you. All righty, over to James. James, perfect.
Yep, was searching for the mute button. Hi all. Yeah, thanks so much for joining. Yeah, so it's been a number of years since I've actually presented, so bear with me here. I don't have a ton of content to go over, and I'm going to do my best not to go over. So yeah, bear with me. To start out, as I was reviewing my slides over the weekend, I realized that I missold what we were doing. Our entire knowledge graph is just shy of 2 billion nodes, but when I actually looked at our Memgraph stats, we only have 1 billion nodes set in Memgraph. So yeah, false advertising there. But I think that the core takeaway still applies. So yeah, kind of a scene setter here, what we're doing at Sayari. Basically for the last number of years, we've been building out a very large knowledge graph of, global corporate ownership and trade. This is a data set, and a whole, suite of products that we're building, to do stuff like, detect money laundering, combat financial fraud. Sanctions evasions was one of the kind of very early core use cases. It's all just has to do with, can you easily understand, stuff like, shell companies operating on behalf of, black market or gray market, activities. And then more recently, we've got into the, supply chain and trade world. And that, relates to forced labor, or, again, kind of sanctions regimes around, import-export controls, weapons proliferation as well. So, yeah, very broadly, what are we talking about here? Basically, Sayari ingests data from currently 568 different sources from around the world, over 200 countries. These are very disparate data sources. Some of them are, HTML web pages that we're scraping. Others are PDFs that we're acquiring. Some of them are bulk data sets, CSVs or some other, more compressed data format. So a very heterogeneous collection of data that we then parse to a standard ontology. We resolve it against itself. We do some level of enrichment around translation and geolocation, and then that basically produces our knowledge graph. And in that knowledge graph, as I mentioned earlier, we have just shy of 2 billion entities and over 7.5 billion relationships. So it's a very large, knowledge graph, corporate ownership and control. And so like, what does that look like? Kind of trivially, this is what it looks like. This is showing, some very kind of simple, high level ownership structures. We see a lot of shareholding relationships, and then there's, family relationships and whatnot, which can convey, similar levels of ownership and control. But as you zoom out, this gets larger and larger, right? And I mean, this is still only 1,000 nodes. So multiply this by many orders of magnitude to hit our entire data holdings of 2 billion nodes. It's a very large data set. So yeah, I think this is a good way to kind of follow up on Maya's earlier point around the difference between on-disk transactional versus in-memory. Yeah, I guess I really appreciated that setup by Maya. I think this is kind of a good point to really kind of tap into that question of like, does Memgraph not work? Does Memgraph's in-memory data model not work for large, applications at scale? Yeah, that's something that we've been working on for a while now, and yeah, I don't know. I think we have an interesting answer to that. It's not without nuance, but yeah, that is a good way to kind of preface this whole thing. So stepping back about knowledge graphs in general, this is kind of an overloaded term. A lot of people use it to mean slightly different things. But what we're talking about here basically is in reference to a more, say, trivial data set. Often if I have to, I'll like compare it to like how you would model a blog or whatever, which has a very simple, data model. You have posts, you have authors, there's not a whole lot of data on each post. You can kind of sketch that out on a whiteboard in, 30 seconds or more, versus a knowledge graph, the type of data that we're working with. Two key things separate it from, broadly speaking, from other kind of data domains. Number one is a complex ontology. So we have 12 different entity types. Chiefly, that's companies and people. I don't know if that's 60 or 70% of our data, but then we're also dealing with stuff like property ownership. And so yeah, we have a property, real estate entity type, and we have court documents, and we have aircraft, and we have container ships, and we have financial securities, on and on. And then connecting all of these entities, there's 38 relationship types, which, again, is kind of this balance between, modeling everything as its own little unique flower versus trying to find some, higher level, simpler schema to roll everything up into. But again, basically, these all kind of revolve around either trading relationships, ownership relationships, control relationships. So stuff like directorships or someone sitting on the board of a company, or familial relationships. But yeah, really the key one there is ownership, shareholding, beneficial ownership. And then finally, yeah, we have a bunch of different attribute types on each of our entities. This is everything from a name to, maybe a tax ID to, addresses, contact information, et cetera, et cetera. So that is one element that really kind of sets off, the problem space that we're working in. The other one is that it's hyper relational. And so, yeah, this means that, it's, if you were to put this in a, relational database, it would mean that you'd be doing a lot of joins. That's kind of the trivial way to think about it. And it's also unpredictable how those joins are going to, perform, or much less predictable. So for instance, our average node degree is, 2.5, 2 to 3 related entities, but then you get these super nodes all over the place that can, easily be, 50,000 relationships. And you absolutely see that kind of distribution here. You have most entities just related to a few other entities, and then you have these super nodes. And this leads to some very unique problems in how you want to go about crafting queries and how you can predict or not predict performance. So yeah, briefly also wanted to touch on kind of how we got to where we are. Basically, we started out evaluating a lot of different databases. This was, 4 or 5 years ago at this point. We looked at Titan and Janus Graph, which uses the Gremlin query language. We looked at Stardog, which uses the Sparkle query language. We looked at dgraph, which uses GraphQL. When we launched, we started out with Neo4j, which uses Cypher. That didn't scale for what we were looking for. Ultimately, right, if we're looking at ultimately 1 to 2 billion nodes, Neo wasn't holding up there. We switched to TigerGraph and then kind of paired that with Cassandra about halfway through. And then when we started running into issues with TigerGraph, we switched to Memgraph. And that's where we are today. Basically, we have a Memgraph database that pairs very well with a Cassandra database. And then also there's other workloads that are handled by stuff like Postgres and Elasticsearch. So I'll definitely dive into point 4 here in a later slide. There's a lot to talk about here, but also at the end, if anyone wants to, I have a lot of opinions, right or wrong, about the graph database space. So happy to go back into this, everything from query languages to platforms and where we're going with this stuff. But moving on briefly, this is really kind of the meat of what I wanted to talk about, which is this question of like, what exactly can you do with memgraphs in memory analytic mode? And I think, you noticed that in Maya's slide, really the pitch there is, you can kind of use this as a background process to, compute analytics over your data. But then ultimately you're going to load it into, some other database that you expose to a customer or whatever, largely because, without analytic guarantees, without ACID guarantees, the question arises, like, can you, expose that to end users directly? And then the second question is, okay, it's all in memory. Like what is that going to, cause issues around scaling and whatnot? We've taken this in a slightly different direction, which is, why I appreciated her slide kind of, setting me up here. The answer to both of those is actually, you absolutely, in our case at least, you absolutely can expose this directly to end customers. We have end customers running live queries against Memgraph, fronted by an API, but still their queries, their requests to us are hitting Memgraph directly. And absolutely, I mean, I think as you can see, 1 billion nodes, absolutely not a trivial workload. And this is, all living in memory in Memgraph. We haven't even had to touch the, on disk transactional mode. This is all in memory. So the big kind of like, the thing that I'm dancing around here is like, how does this work? The big thing that sets us apart is that these workloads happen to be read only. So it's very similar to what Maya described, except there's a bulk load, and that is the only write to Memgraph, and then we expose it in analytic mode to live queries from end users. You actually don't need ACID guarantees because it's a read-only. It's in read-only mode at that point. I'll just to kind of touch on this in more detail. This is absolutely a very powerful mode that Memgraph advertises, but it is not the only mode for analytics for running the database in analytic mode. Absolutely, in this bottom left right here, this doesn't have to be another database. This for us, this can be the client itself, and the big caveat there is if you're running read-only workloads, you can expose an analytic database directly to the end user. So also just stepping back here and considering kind of what that actually means. I want to also kind of talk about the difference between OLTP and OLAP. I always kind of forget what those mean specifically, but most databases that users are used to thinking about, Postgres, kind of, et cetera. What is it? Something transactional modes are run in OLTP modes. That's what most people think about, and that means you are accessing. Usually, it's a small amount of data, high throughput, low latency, but only a small amount of data. versus OLAP analytic databases like, we use BigQuery a lot, Snowflake, Databricks, Redshift. There's tons of them. These are queries that are, they're workloads that are often that are rarely exposed to end users. First off, usually this is kind of a background process, and rather than low latency and a small amount of data that you're accessing, usually it accesses a huge amount of data, and you're not looking for latency. You're, because it's a background batch process, you're just looking for essentially throughput. You're optimizing throughput. So what we have done, though, by running Memgraph in a read-only analytic mode is we split the difference between these two, and that has worked very well for us. So we are very much, serving live queries to end users, similar to an OLTP database like Postgres, but at the same with the same kind of roughly the same latency expectations. But we're also hitting huge subsets of our graph to back each of these queries. That is a very powerful mode to really get the scale and the performance and the kind of analytical richness of a OLAP database, but many of the performance guarantees of a OLTP database, with the big exception of ACID. We've given up ACID guarantees because this is a read-only workload. Talking about kind of like, how does this actually really work in practice? What does this look like for Memgraph? Operating characteristics here for us. Basically, we actually have two separate graphs. One with the main one with 1 billion nodes, 1.2 billion edges. The point is, this lives in a little over 500 gigabytes of memory. That's not small, but that's also like very doable given modern infrastructure. You can rent a machine from any cloud provider with double this memory. This is not a hard price point. It's decently expensive, but it's also way less expensive than what we expected. This is not a major hit on our cloud spend. It's not something you can probably do if you're running a personal project or whatever. But absolutely, like these are workloads that are not trivial, but close to trivial to run, on modern infrastructure. So anyways, this is at least one point that really kind of calls into question, like, can, Memgraph's in-memory mode scale? Like we have not had issues here. And then to illustrate this even further, our trade graph, which is really, customized around some much more kind of bespoke trade-based queries. This is much smaller, but it's also not trivial, over 12 million nodes, 24 million edges. This is a large data set, and this fits into, 8 gigabytes of memory. Like this is really, absolutely tractable. I guess there's kind of 2 points here. One is Memgraph is very good at compressing data in memory, much better than other databases, very much better than Neo, for instance. This was one issue that we were running into, right? Neo's whole selling point is like, well, not their selling point exactly, but like, they're they can, you can throw a whole lot of memory at it, but ultimately it all sits on disk. And so you would think that would be a mode that would scale better. But their memory usage, because they're not trying to optimize for that, is not good. And you have to throw a hell of a lot of memory at it if you want to, get all indices in memory. They do not compress. It does not compress well when loaded into memory versus Memgraph, which absolutely does, right? If you're under 9 gigabytes of memory for 12 million nodes, like that is a really good characteristic. And sorry, there was one other point here. Sorry, I was just reviewing my notes. One other element that I really wanted to call out around this kind of whole, in-memory operating model. Even Maya called it out earlier herself. it's like when you hear in memory, people usually think of like one of two things. Either it's like, oh, this is basically like a library. We should kind of think of this as like network X or whatever. Like, you're going to maybe load a portion of your data set into it, or maybe you're going to use it if, you have a trivially small data set, but this is like a library, not a database. And then the other way to kind of cast what is a, in-memory database? What does this look like? It's like, oh, well, it's actually like, sure, it's a proper database. It's not just a library, but it's for very like bespoke kind of workloads like Redis, right? That performs incredibly well, but is really, limited in what you can do with it. Just calling that out because, that clearly, as I think you can see here, that is not the experience that we've had. We are treating this as a proper database. And it's scaling incredibly well, and we're throwing, non-trivial workloads at it. But there are major caveats here. So not to, bury the lead, but one is that this is a caveat less about the OLAP part and more about like, what does it mean to store a very heterogeneous knowledge graph in Memgraph? And one element that we run into, again, this is less about Memgraph and more about our specific use case. But performance is very variable. As you can see here, average performance is actually quite good. What is this? A second and a half response time, again, for very expensive queries that are likely hitting, hundreds of thousands, exploring a graph space of hundreds of thousands or maybe millions of nodes. 1.5 seconds is a really good response time. But if you look at the 95th percentile, this jumps up to, 5 to 10 seconds. And it's very variable at the 95th percentile. So that's all to say, right? Why is this happening? It's because many of our queries are hitting, decently sparse elements of the graph, and perform well. But every once in a while, a user is going to ask for, say, the ownership structure of a node, and it's going to have 10,000 owners, and some of those holding companies are going to have 10,000 owners themselves. And it just happens that they've queried a very dense part of the graph, and performance drops off. So that is a kind of key consideration. Again, more about our specific use case, but I can jump into that more in a second. Watching time here, so I'm going to try to move pretty quickly through these next few nodes, these next few slides. But in our trade graph, we kind of see a similar performance characteristics. Under 1 second for most queries, but every once in a while they'll jump to 5, 10, 15 seconds. So how do we handle that? This is the meat of everything here. So I'll try to not move too quickly through this. But like the biggest element about how to make this work, this applies to all graph databases. This is just kind of is managed cardinality. It's very easy. It is trivial to write a query that will traverse millions of nodes potentially, a very non-trivial subset of your entire graph. In particular, if you're doing these, we do a lot of kind of breadth first searches throughout the graph, starting at one seed node. And again, if you happen to hit a node that's in a very dense part of the graph, this can be very large. One of the big, basically, again, to bury the lead here, the big question is, how well can you think about the relationship between the edges and the number of paths that they're producing? So to kind of illustrate how this type of rather trivial query, very simple to write, just traversing out over shipment relationships, looking for indirect shippers. What this is actually doing in many cases, if you have multiple edges between two nodes, you end up with, in this case, a total of 27 different paths through a very trivial subset of the graph. Right, this is something you have to consider. Really, you probably don't want to be producing every unique path through this graph. You want to be much more, you want to manage that cardinality a lot better. So this is ultimately where we ended up. We said we need to collapse these multi-edges down, and all of a sudden, rather than 27 edges in this kind of demo case, we end up with only 3 edges. And in order to do that, looks a little messy. So apologies, right? If this is where we started with a very simple BFS query, and this is where we ended up, we're basically doing the same thing, except manually running multiple matches to traverse out. So there's a lot more match clauses rather than one BFS match clause. And then, we're collecting and collapsing all of the edges between each node pair. That's what you get on line 3 with AB collect R1. And that basically produces this outcome here. Ultimately, it's a lot more kind of bookkeeping to do, but it works actually rather well. This is kind of another point there's a few more considerations here, but honestly, it's more or less the same idea. Managed query search space, right? If you are traversing out, 2, 3, 4, 5, 6 hops in a dense part of the graph, you're going to hit 100,000, a million, 10 million nodes very easily. There's again, you have to manage cardinality in order to think appropriately about this. The other very useful additions that Memgraph supports, being able to return partial results. This is not unique to Memgraph. Elasticsearch has a similar feature. But yeah, that's very useful. You can say, well, in theory, there's 10 million nodes that we would have to search. We're going to time out when we hit maybe 1 million nodes. You're still going to have a lot of really useful information for your user. They probably don't even need to know, the full depth of the graph if you've already found results, within 1 million nodes. So, return what you can on timeout. Even better, in order to get more predictable response times, is limiting the number of edges traversed. This is a new feature that I think just landed in part in the recent Memgraph 2.17 release. So this has been around for 3 or 4 or 5 days. We haven't played around with it yet, but we've definitely been watching its development. And then finally, just carefully consider multi-graphs, this idea of having multiple edges between 2 nodes. Okay, I'm gonna have to speed myself up here. The other optimization is basically treat Memgraph as an index. What this really means for us is we don't store everything in Memgraph in the same way that we don't need to store everything in Elasticsearch. We need to support full text search over our data, so we store some of our data in Elasticsearch. And similarly, we need to support complex deep queries, and we store all of that information in Memgraph. But ultimately, Cassandra or whatever, we have another different data store that is our master data store. Again, that kind of gets back to this question of how do you truly deploy Memgraph at scale? You don't have to write everything to it. It doesn't have to be your master database. And then finally, this is my last slide, I promise. Manage decompression and serialization. This is the type of thing that doesn't really matter if you're just looking at small subsets, because decompression and serialization is very fast. But if you're doing it millions of times, it becomes very slow. So we've been experimenting a lot with integer enumerated types. I think Memgraph is working on enumerated types natively, so that'll make this even easier. And then again, don't store everything in Memgraph. Only return the properties that you need, etc. Okay, I'm a little over time, but I think there's still time for questions. I'll call it there.
Thank you very much, James. No, you're not over time. We still have time, but
Great.
We have a lot of questions. So, we'll get to those in just a minute. First of all, I want to say this is a great and interesting presentation. I like the way you set up what a knowledge graph is, and then use that for risk analysis or risk intelligence, right? So give me 1 second. I'm going to actually share my screen. There we go. All right. Before we go into the Q&A session, I'd like to remind the audience to take a second poll right now. Do you have a graph use case? Does it require in-memory analytical processing or in-memory transactional processing? All right. And now I'm just going to give you a few seconds. So I just want to say, for those of you who are still who still haven't asked any questions, note that there's a Q&A box on the right-hand side of your screen. That's where you should add your questions. And James, are you ready? I'm going to remind you to take yourself off of mute.
Yes.
So we can go through this. And I'm just going in any order that I see these questions. The first question is, have you thought about data replication and having read-only instances in analytical mode?
Yes. Yeah. Absolutely. Right. So Memgraph now supports, a high availability mode. We are running a high availability cluster, but we're not even using that, the native capabilities there, because absolutely, once you have a read-only setup, you can just deploy a bunch of independent instances, put a load balancer in front of them. There's if it's a read-only instance, there's no need to, have a RAF protocol or whatever it is running in the background that, syncs updates. So yes, absolutely. That's how we do it. We run in, read-only clusters.
Thank you. The next question is, as far as I'm aware, ontologies are predominantly used by the RDF data model, not labeled property graphs, which is what Memgraph is based on. How did you adapt or simplify your ontology, which is usually atomic and contains first-order logical statements, for labeled property graphs?
Great question. When we started out, we were kind of experimenting in the RDF space with, databases that use the Sparkle query language. I used to work a lot in the kind of knowledge graph or semantic web space. I guess I'll say that the semantic web has popularized and kind of owns the idea of an ontology. But broadly speaking, there's nothing that prevents you from using that idea of an abstraction in other places like labeled property graphs or whatever. So I mean, the big thing that we don't have is any type of like reasoning engine or whatever. There's no OWL statements, nor is our ontology explicit in the same way that right. It's not like we write our ontology to Memgraph in the way that you would write your ontology to a semantic store. So I guess, what we're doing ultimately is more just kind of like the idea of having a ontology that explicitly says, here's the type of relationships that can join these two types of, entities. What those like ontology constraints are enforced outside of the database. That's maybe another big difference, is that, that's all application level work to make sure that we don't, add a, family of relationship between two companies. That's all part of a different system, not native to Memgraph. It's kind of maybe it's a bastardization of the approach, but it's taking the same kind of high level concept of having an ontology to describe a complex data space.
I think you explained that really well, James, because coming from the RDF world to the property graph world, there are differences, obviously. But it's really how you store in a triple store versus a property graph, right? And I think you outlined that really well. This question, I think, is an important one. Can you talk about your ingestion pipeline? For example, do you stream writes or do you perform a bulk load?
Yes, we perform a bulk load. That's kind of key to the whole, read-only data mode, is that we do a bulk write to the database when it's in an offline mode, and then we make it available and switch over all of our services, our APIs to point to that new instance. We do that across all of our databases. For what it's worth, all of the kind of upstream data processing work of ours, all of the infrastructure that produces our knowledge graph, that's all running in Spark, which is this hugely scalable framework. It's done really well for us, we've found there are some downsides to not having a streaming approach, right? Kind of the benefit of bulk over streaming. In addition to this idea that all of your databases can be in a read-only mode after you're done with that bulk write, the other benefits is like throughput. It's a lot more efficient to just rewrite everything all at once versus kind of stream updates into a live database. Streaming updates is slow, but the obvious trade-off is, essentially it's a latency versus throughput trade-off. With a bulk write, you get crazy throughput, almost unlimited throughput, but you can kind of think of your write latency. In our case, we rewrite all of our data. Depending on what system, it's either every 2 weeks or sometimes it's every day. But you could say basically our write latency is a day. That's pretty slow, or even 2 weeks, that's really slow, but we get to write billions of things every day or every 2 weeks.
I think that kind of answers this next question that I'm going to ask you. With a 10-hour load time, how are you updating the database? I would imagine you couldn't, update the database in production in analytical mode. Do you rebuild from scratch and swap out?
Exactly. Yep. That's the whole point. Right. We're rerunning our resolution pipeline. That takes a number of hours. We're re-enriching parts of our data. We're ingesting new data. And then we write everything to all of our databases. And, end to end, that takes, something like 24 hours for a full rebuild. And then we, that's the build that we only do every 2 weeks. And then we kind of have smaller, mini batches, you could call it, writes that go off, up to once a day.
So a question just came in that kind of talks about this again. How do you sync the updates to all of the replicas? Something in Memgraph, or do you use some kind of coordinator?
Exactly. We don't need to, we could, but we don't need the overhead of Memgraph's native high availability replicas. Basically, the coordinator in this case is the bulk write that Spark kicks off. But you could, you don't even need Spark for that, right? It's pretty trivial to just say, hey, do a bulk write rather than to one machine, do this bulk write to 3 machines or 5 machines. That's pretty straightforward. And again, the complicated part around replication and clustering is keeping them in sync. But if you don't have live writes, you don't have to worry about that. You just have to make sure that the first bulk write, all of those succeed. That's pretty trivial to do. And once you've done that, you've kind of guaranteed consistency, till the end of time, or until you tear the databases down.
Cool. I want to get in one last question because I think you'll enjoy this one. Which tool did you use to visualize this large data set? How did you manage transferring large amounts of data as a result set? Yes,
great question. The visualization tool, we've spent a lot of time on that. This really interesting space around, web-based network visualizations. We developed our own open source library that uses WebGL to render out large graphs. It's called Trellis. Look it up at Sayari/Trellis on NPM or wherever. We're definitely pretty proud of that. It's one of the few open source WebGL. I think it's one of 2 open source WebGL network renderers. Honestly, there's not as much work in that space as I feel like there should be. D3 is the big kind of classic one, but that's really only renders to SVG and Canvas. Anyway, so we're very proud of Trellis. Please check it out if you're interested. There's a few other players there. But to get to the second part, because that's also very interesting. How do you get all of large amount of data into the browser? Actually, we don't usually. The way that our queries run, we're searching a very large space, doing a breadth first search over a very large space. But usually, we're really only returning a small number of paths. Small being, can be 10, can be 100. In some cases, actually, it's like a couple thousand, and that does result in some, latency issues. And we're looking at, better response formats to handle that. But largely speaking, even if you're searching millions of nodes, you really only want to be visualizing tens, hundreds, thousands, maybe up to 10,000. But anything beyond that is going to be very hard to visualize. Not even just performance wise, but like it's hard to visually grok that much information at once.
Well, thank you. We're at time right now, so we've come to the end of our webinar. I'd like to thank our guest, James Conkling, for this really informative presentation. I'd also like to thank you, the audience, for sharing the last 45 minutes with us. I hope you learned a lot from this webinar. I sure did, for sure. I sure did. Don't stop here, though. Join our Discord to continue this conversation. We're always ready to answer your questions. I want to give you a quick reminder to join us for our next webinar on June 25th, where Michael Marginelli from Smart Buildings will talk about constructing a digital twin using Memgraph. That promises to be a really good one as well. Till next time, ciao.
Thanks all.